having me. So I realized today that I didn't have a picture of the Notre Dame UCS student chapters in my talk, which I should have. So we were the 2023 outstanding student chapter of the year. So and you guys are 2022, so we should probably collaborate. Yeah. There's probably a lot of things we could do together. But thanks so much for having me. I realized after I made my talk that I think my abstract, I changed what I decided to include in the talk between writing the abstract and putting the talk together. So it'll be some on polymers, and then some stuff at the end that's not about polymers. But my group. But my group works on various. So my group works on various different areas that I don't have time to talk about today. But we've done quite a lot of work in metal electric deposition, especially magnesium metal, lithium metal, and sulfur electrochemistry. And then the bulk of my group works on studying ion transport and soft or composite-like media. In addition to what I'll talk about today, we've had a heavy emphasis in all solid state systems. And more recently, we have a little bit of work in separation membranes and also fuel cell membranes. Okay. All right, and to thank the people that did the work, the research I'll talk about today in the first half was completed by Hunter Ward, who's now at Naval Research Laboratory, and MoChA, who's working for Exponent back in China. And then the second half of my talk will be on the work of Lingyu Yang, who's very, very close to defending her dissertation. All right, so I think, you know, a lot of us that work in electrochemistry are motivated by sustainability. So I won't say much about this slide, but if you're not familiar with this flow chart, this is an energy flow chart produced every year by Lawrence Livermore National Laboratory. And there's a lot of information on it, but I'll just point out a few things. So on the left-hand side of this flow chart, you can see primary energy sources that we use in the United States, and the magnitude of those was roughly equivalent to the scale of these bars here. And then on the right-hand side of the chart, how the energy is used. And what I'll just point out is there's a lot of different ways that we generate electricity as a secondary energy carrier. Okay, and many of these ways that we can generate electricity are low carbon emission, if we choose to use them. And then the other thing I'll point out is that the transportation sector of our economy is actually heavily dominated today by these other energy sources, which we know are carbon emitting. And the other part of this using combustion engines is that they're very inefficient. So you can see here the scale of the energy that's wasted. So this is energy dissipated as heat. Whereas the energy from the combustion engine that goes towards actually useful mechanical work is relatively small. Okay, so many of you know that we're looking towards moving to electric vehicles so that we can change this scheme here. And so I'll talk about batteries today. And so if you don't work in batteries, they're very, very important for the reasons I just mentioned for offsetting combustion that's used in the transportation sector, be it small electric vehicles or even larger scale transport. And they're also very important for what's called load leveling, or modulating the intermittency of electricity generation. So we talk about large scale, more green electricity generation that's often intermittent, but we have to balance the amount of electricity going onto the grid and the electricity that we're using, and this can be done with storage. All right, and so for the folks in the room that don't work on batteries, I just wanted to show a couple schematics to kind of ground you in what a commercial battery actually looks like before I talk about materials. So this is a cross-sectional schematic of a commercial lithium-ion cell, and I would advocate this paper if you haven't read it before. It's very, very excellent. And so what they've shown here is really the true length scales of the different parts of the device. And so every battery is composed of the two electrodes, right, which are separated by the electrolyte. And what they highlight in this schematic is that in commercial lithium-ion cells, both of these electrodes are very dense composites, right? And so they're highly filled particulate systems where the active materials are in the form of particles, and they are held together by a small amount of polymer binder and mixed with a carbon additive, and they form this very thick tortuous layer. And that's on each side of the cell. And then the electrolyte resides in the middle, but the electrolyte also has to fill in all the pores within the electrodes inside here. And this schematic shows an R&D type case for magnesium sulfur cells. Magnesium sulfur electrochemistry is very challenging. I'll just point out in this cell, you can see here that instead of graphite on the anode, we've replaced it with magnesium metal. So by using the pure metal, you can see you can really reduce the scale of the anodes. You don't need very much material. But magnesium sulfur electrochemistry is pretty challenging. It only happens with this substantial excess of electrolytes. So people making these research cells are using really, really thick separators and lots of excess liquid. And that kind of diminishes, the gains that you make in using this small anode in order to allow this sulfur to function here. And because I promised talking about polymers, I'll just point out a couple common themes between these two systems. So like our commercial system and a potential next generation system is how we currently make these are with non-porous non-functional, but porous like inert separators, right? So in the commercial cell, we have microporous polymer film. So it's usually polyethylene or polypropylene or tri-layer ligaments of those coated in metal oxide particles that are used to just separate the electrodes. So really the function of the polymer there is just so that you can bind the electrodes together and you don't actually touch, but there's holes in it, and then we fill in those pores with an aprotic organic electrolyte. And so for lithium-ion systems, this is an organic carbonate mixture that you then dissolve salts in. But for any type of metal sulfur cell, we're usually using ether type mixtures. So the solvents are different. They have different properties, but they're all relatively volatile with higher vapor pressures, and they're flammable. And then polymers are also used in these cells, as I mentioned, as the binder. And they're very important in our commercial designs for maintaining mechanical integrity, right? So as intercalation and de-intercalation happens, so as the lithium goes in and out of the particles, there can be volume changes. And so the binder is important for holding all the parts together, so we ensure electron transport. Whereas so the porous layer here does not get disconnected from the current collector, and so that none of the particles are disconnected from the carbon. And the rate capability of these cells is limited by both electron transport, but also the active ion transport. And it's important that the ions don't just move between the top surfaces of the electrodes, but that the ion can actually get in within the depth of the electrodes fast enough. And if you're interested in limitations on ion transport, we wrote a review article in JES a few years ago on this. We really combined a lot of literature. All right, so because my abstract title was about polymers and batteries, I figured I'd give a very brief overview in case there's any people that are polymer scientists or interested in polymers in the room, how else they can be used. And so today I'll talk about polymer-based electrolytes. As I just mentioned, polymers are also used as binders in the electrodes. And while we currently use a fairly inert polymer, so PVDF, you might have heard it's a common binder that's used, there's a lot of research ongoing now to create more functional binders for battery electrodes. So PVDF is soluble in organic solvents, so it would be greener for processing if we had aqueous or water-soluble binders. It would be better if our polymer binder was functional and was a good SEI former, so we get very advantageous surface chemistry. If the polymer itself was electrically conductive, this would be advantageous, or if it was absorptive for maybe species that are generated that we don't want to transverse in the cell, that would be advantageous. And then there's been excellent work recently in the research literature that's been done on creating artificial SEIs or artificial interfaces on the surface of active electrodes. And so this is creating a surface layer in order to control the interfacial chemistry that happens. And this can be done with polymers as well. And then in sulfur type batteries, there's a lot of intermediate species that are formed. So my group and many others have been working on creating interlayers or surface coatings that kind of modulate the transport of these intermediate species on the cell. And there's been a lot of work in the last few years, and particularly on trying to swap out the inorganic electrode materials with organic materials. And of course, these generally result in lower energy density. But the thought is that these could be organic electrodes, you know, they're organic. And so we could potentially make them with very abundant elements, and that they could be very low cost, potentially even biodegradable. And then in terms of large scale energy storage for grid load leveling, flow batteries have been researched for many years, of course, in our pilot scale and some small scale commercial applications. And in flow batteries, we have two different compartments with the active materials dissolved in a liquid in a traditional configuration, and these are separated by a membrane. And actually, the crossover of active components across the membrane reduces the capacity of the cell. So designing better membranes that are also cost effective is very important. So with that, I'll move into talking about electrolytes. And if you're not familiar with this space, I just wanted to ground all the students, let them know like how broad the battery electrolyte literature really is, how much work has been done in this area over many decades now, a tremendous amount of work. And really in all types of flavors of materials chemistry. So whether you really like liquids, or if you like inorganic solids, or if you like plastics, there's been a lot of work done in all of these. And I would say in all combinations of these materials. So any way you can think of taking these different classes of matter and combining them, people have done to try to create a somewhat better electrolyte, whatever that means for the particular application or particular performance metric that they're looking for. And inorganic solids, of course, there's a lot of startup companies working on all solid state inorganic systems today. But actually, the most successful one so far has been LiPo with relatively low conductivity that's been used only in the thin film case. This is hard to scale large. Our current commercialized lithium-ion systems, of course, use liquid electrolyte, but in the 1990s, Belcore commercialized what they call a plastic lithium-ion cell, which actually contained a sort of polymer gel electrolyte. But that didn't maintain as much market share as our current system, where we have this inert micropore separator. And then within the polymers case, there's a company now, Group Solutions, in France, where they have all solid polymer batteries that are being used for transportation. But of course, the conductivity is lower in those electrolytes, so they have to operate them at much elevated temperatures. And of course, there's been a lot of work that's been ongoing in composites. And of course, the goal is by combining materials always, so we can get something better. We can't get with one sort of material. And so with that, I'll tell you about today the work that's been going on in my group with regards to studying ion transport, towards getting towards controlling conductivity or other properties of the electrolyte. And we'll look at two very different classes of battery electrolytes. So first, I'll tell you about single ion conductors. And then at the end, I'll tell you about charge transfer complexes, which are a different case of non-polymeric electrolyte. And I don't know how I can time. So if you can let me know as we're going along, that would be awesome. Thanks very much. All right, so first, so what is a single ion conductor? Okay. So a single ion conductor is an electrolyte where only one of the ions move. Now, if you imagine a fluid, just any fluid that you dissolve salt into, so like a commercialized lithium-ion electrolyte, you have multiple species. So you at least have two different species, a positive species and a negative species. And in the presence of the electric field, both of those species will respond and they will move. And when that happens, because only one of the species is reactive with the electrodes, over time, you will develop a steady state ion concentration gradient here. Okay. In a single ion conductor, only one of the species is able to move because of electroneutrality. Well, electroneutrality must be attained. This ion concentration gradient does not form. Okay, and you get more uniform ion distribution. And when talking about polymers specifically, the way that we achieve this is by covalently tethering one of the ions to the polymer backbone. And then the polymer is not able to move long range, then that ion isn't able to move either. So if we're talking about a lithium ion conductor, a sodium ion conductor, you would covalently bond the negative charge to the polymer. And then only the cation would be able to move. Of course, in these systems, the cation transference number can then reach unity. It's not unity though if the polymer is able to diffuse, it's in a dilute solution and is able to move. All right, and so why have people been going after single ion conductors? And so this lower ion concentration gradient theoretically will allow you to have higher charge discharge rates as long as the active ion conductivity is maintained. And there's experimental evidence to show that this is true, that this works. And then there's a lot of knock-off effects. So when the ion concentration gradient forms, the anions stack up to the interface, electron interface. And so this increases interfacial impedance. When they're up against the electron interface, that's also where electrochemistry happens. So the anions can break. Okay, and this can create resistive surface layers. And so you get cycling behavior if you can mitigate this if the anion composition was a bad thing. And there's also been a lot of research in the literature talking about how reduction of these depletion zones where we don't have lithium due to the concentration gradient, reducing those can help to mitigate somewhat lithium metal dendrite depletion. All right, so that's single ion conductors. So within the polymer literature, there's been a lot of work to create plastics that can function as single ion conductors where the cation can move fast enough to make these, applicable for real batteries. And so there are two different classes of what's been being worked on. And the first class is the majority of the literature. I'll call them solvating ionomers. And so how these polymers work is that they all contain part of the polymer is polar, okay? And the polar matrix is very important for ion solvation. So lithium here in the schematic, you can see it surrounded by, this is actually polyethylene oxide. You're familiar with that chemistry. But these oxygen atoms here have pairs of electrons on them that interact with the lithium cation. So lithium and polyethylene oxide likes to make a shell of like 4 to 6 oxygen atoms. And so how these polymers here are designed are that they all have some polar part, usually this polyethylene oxide or polyethylene glycol part. And then they have these tethered anions. And you can see that these anions are really big. So there are a lot of atoms. And that's very, very important because the anion being large and having many atoms means that the electron is highly localized over many atoms. And so the binding energy between the anion and the lithium is smaller. Therefore, it's easier for the polar polymer chains to separate, to totally solvate the cation and separate it from the anion. And then once the lithium is solvated by the plastic, its ion transport, we more so understand this part. Once it's separated from the anion, the polymers move sequentially, so they wiggle back and forth. So with increased temperature, they wiggle faster. And in the presence of an electric field, the lithium will kind of move between coordination sites as the polymers move. And so the rate at which the lithium moves in this type of environment is totally coupled to what we call polymer segmental dynamics, which is how fast the polymer is wiggling like this. And so we know kind of how to optimize these systems. And in the past couple of years, there have been some advances. And so I'll just point out a couple kind of preeminent works in literature right now. And so Schaefer and Jeremiah Johnson's group published on this polymer in 2021, where what they did was they created a tunable anion here that's tethered to the polymer backbone. They mixed this with polyethylene oxide. But here, these R groups, they were able to swap them out for different chemical functionalities, which made the anion better to interact with the polyethylene oxide. So if the PEO chains come closer, because these R groups like them, then the lithium is easily able to go into the polymer. And then the other advance that was made is this one shown here that was published, I think in Nature Materials last fall. And what this group made was, instead of a lot of these polymers are block copolymers or they're random copolymers, they actually made a perfectly alternating polymer. And so they were able to place every single anion directly near this PEG chain. So again, they did the ethylene oxide units very, very close by to the lithium, and then it's able to be separated and then it moves. So these have the highest conductivity so far. But unfortunately, the conductivity of the lithium in these systems is always limited by the polymer segmental dynamics. So the best we could ever possibly do is what you get when you take lithium salt and you dissolve it in PEO. And we know that that's not good enough for room temperature applications, really. Okay, so they always have to operate at elevated temperature. There is still some fundamental questions about these systems, like really local effects, molecular level effects of like dynamics and chemistry, and how you get ion pair dissociation and ion migration. And there's still some important challenges, research challenges, I would say, with regards to characterization. So it's still hard for us to characterize and to know in any given system, like what the population distribution is of lithium in the system. Like what fraction of lithium has a total like polymer solvation shell? What fraction of the lithium is coordinated with the anion and has a mixed solvation shell? So these are still really important questions. And then there's another class of polymers that people have been studying more recently in my group as well, where the polymer itself doesn't have any polar component. And so the ions cluster all together. And it's sort of more like the local anion or cation environment would be like if you had like a dry surfactant, basically. And what we're trying to understand in these sort of studies is you can get decoupled lithium ion motion. So if you can get the lithium to move, then it can decouple from the segmental relaxation of the plastic and actually pop. Because of course, there's many inorganic materials that have very, very high lithium ion conductivity. Okay, so we're trying to understand, can we engineer that into a plastic type material? And I just showed a structure of like one of the polymers we've been looking at. So far, we found that these systems still have very low conductivity, so they're not competitive, but we're really trying to focus on the mechanism and understanding how the lithium pops, or what we can do to get it to pop in these types of plastics. Okay, so then what I'll tell you more about today is our recent work on single ion conducting gel polymer electrolytes. So the previous slide I was telling you about polymers where there's no liquids, it's just the plastic, okay? And those suffer from too low ionic conductivity. And we know we can improve the ionic conductivity if we add liquid, okay? So that we get the lithium solvated by liquid molecules, so it moves by a vehicular motion. Okay, so if we add solvent, we're definitely getting higher bulk ionic conductivity, but there's other benefits as well. So the material, the plastic is softer, so that gives better contact with electrodes and in general lower interfacial resistance because of that improved contact. We can still make the system be single ion conducting and have no anion motion, as long as the polymer, when it's swelled in the liquid, is cross-linked or somehow entangled so that the polymer chains can't really translate. And so then we still eliminate the ion concentration gradients, so that's good. Of course, when we introduce solvent, we could introduce all of the same stability problems that we have in traditional electrolytes, with thermal stability, chemical stability, electrical stability, all super important. And if you just Google gel polymer electrolyte, I guarantee you will find thousands of papers. And most of them tell you that we study gels because they're safer. But there's been very, very little work done to show whether there's really any safety improvement at all. So I would say that's still an outstanding question. So in thinking about creating sort of gel polymer electrolytes, right? So there's lots of other devices where you have an ionic polymer or an ionomer, and it's in a fluid, right? And it acts as an ion conductor. And so fuel cells is a good example of another application where this is prevalent. So several years ago, there were a series of papers about, well, what if you take just the ionomers, or some people call them polyelectrolytes that are used for fuel cell membranes, right? And we exchange out the protons for lithium or sodium or other alkaline ions. Can we just use these, right, as membranes in batteries? And what people have found is that you only get, so you can see the conductivities here, they're like 10 to the -3 Siemens per centimeter. So that's good. That's like getting close to that of a liquid. The problem is you realize that the solvent that they have to use in order to get this high conductivity are not compatible, okay, with most battery chemistries. And so here they use dimethyl sulfoxide. DMSO is an excellent cation solvator, but it's not chemically stable against lithium metal. It reacts with it instantaneously, and it has really limited electrochemical stability, and also has trouble desolvating the cation in the electrochemical interface. Okay, so and the reason why they use these solvents is because without these, so-called excellent solvents that are not typically used in batteries, the conductivity is just still too low. So we really need a different sort of polymer. And I would say, I think one of the kind of leading papers in this area is this one, which I think is from like 2019, so maybe like 5 years ago. And they actually produced a material that one's swelled with ethylene carbonate, which is used in commercial lithium-ion battery electrolytes. This molecule here can give you conductivities on the order of 10 to the minus 3 Siemens per centimeter at room temperature. And I just want to point out some of the features of this polymer. And so you can see here that this polymer has a sort of really rigid backbone. It's a polysulfone, but it's a very complicated system. So it has like hydrocarbon type backbone here, and then it has segments that are fluorinated, and it has these side chains, so it has fluorinated side chains, and then it has these relatively large anions here, so you get lower binding energy with lithium on the end of the side chain. And this polymer, when it's exposed to these types of solvents, forms this sort of nanostructured like membrane, where the hydrophobic backbone of the polymer comes together, and then there's these channels that are full of liquid where the anions reside. And it gives you good conductivity. The problem is that this particular polymers like these are very, very expensive to make. So there's still some work to do there. And my group got into this area on accident. So at the time we were that this paper came out, and then I had a student working in lab on this project here, where his whole dissertation was on ionomeric membranes applied to metal sulfur batteries. And he was trying to really understand some fundamental things about how if you have a polymer membrane, it's in a battery electrolyte, where we have a sulfur cathode, and what features of the polymer would be really good at repelling these intermediate polysulfide species, so they didn't leach to the bulk electrolyte. And so he was making ionomer networks by taking very simple macromonomers here. So this is PEG, for example, with acrylate groups. These are polymerizable groups on each end, so it's a difunctional molecule. These are very cheap, and you can buy them commercially at large scale. And he was polymerizing this one with this ionic monomer, which wasn't available commercially at the time, but now it is, you can buy it. And he was making these cross-linked gels to kind of look at some fundamental polysulfide screening things. And we had a hypothesis that the dielectric constant of the polymer media was really important. So he was comparing this commercially available material with this one here that we made in lab, where this is poly-THF diacrylate, we just have more carbon atoms. So the density of the oxygen is less, so the oxygen atoms are further apart. And we thought that that would be important for how the polysulfides would interact with the membrane. And at the time, we were doing work on those other types of ionomers that I mentioned earlier. And he just decided on his own that he was going to ion exchange these, and he was also working on magnesium sulfur systems. But he decided to ion exchange his materials to the lithium form, and he wanted to study them as single ion bonders, as like a side. So then he brought me this data. And so the first data he collected was when he had these cross-linked ionomers in the dry form. And he got what you would totally expect from literature, which is the conductivity of the ionomer, the cross-linked ionomer with the PEG, is higher than that of with the poly-THF. And that's easily understood because PEG, the density of its oxygens is really ideal for lithium cation solvation. So this should be true. But then he decided to swell these, and he swelled them in two different types of liquids. So in one case, he swelled it in a dual DME mixture. So this is an ether solvent mixture that's commonly used for metal sulfur batteries, but without any solvent in it. He just put it in the solvent. And in another case, he swelled it with a carbonate-based mixture. And what you can see here is in both cases, the ionomer with the poly-THF with less oxygens in the polymer backbone gives you higher ion conductivity. And we were actually kind of surprised by this because PEG diacrylate, like gel electrolytes, are used in the literature. There are like so many papers. You can find, You can find so many. You just Google like PEG, polymer, gel, electrolyte, you're like all over the place. But with just a really simple change by lowering the oxygen density, somehow we're getting, you know, a much higher conductivity. And so he tried to figure out why this was. So at first we thought that maybe there's a difference in how the cation is interacting with the TFSI that's on the polymer backbone. And so we've been doing a lot of Raman spectroscopy in the group. So he applied that in this case as well. And these are the Raman peaks that you get for the anion itself. So TFSI is kind of a bench structure. And it modulates like this, and there's a Raman band that correlates. And this particular anion, its local environment really changes the Raman spectrum. So if you have a cation nearby, or if it has a difference in mobility, you see a change in this band. So we were really surprised that in this case, the band is really similar all the time. So between the PEG, between the poly-THF, and with different solvent environments, the band is really similar. And so we thought that the number of lithiums that are dissociated from the anion is roughly similar in all cases. So this can't explain the difference in the conductivity. And so the only way that you can explain this difference is how the lithium actually interacts with the polymer chain. And so what we hypothesize happens is this. So in PEG, I told you that PEG is really an ideal lithium solvator. So we believe that even in the case when you have solvent in this gel, some of the lithium may be totally solvated by the solvent. And so it moves with vehicular motion unimpeded. But if it flows by and if it's close to one of the PEG chains, we think the PEG chains are sticky, right? And so the part of the lithium solvation shell may exchange for the polymer chain, and the polymer is not moving nearly as quickly as the solvent. So it's kind of temporarily stuck, and right? And the polymer chain is way back and forth, but the lithium's kind of stuck there. And then only if it exchanges out to total solvation shell is able to move vehicularly, which is much faster. Whereas in the case of poly-THF, it's much less sticky. So there's less oxygens and there's more carbon and hydrogens. And so you have a much higher fraction of the lithium that has a full solvent solvation shell. The other difference that we notice is if you look carefully in this data, you see that the magnitude, the amount of increase you get by switching out the polymer for poly-THF, it's actually much better with a carbonate-based solvent. This was extremely confusing to us because the carbonate-based solvent actually has a higher dielectric constant, should be better in solvating. So then the question was, why does the polymer matter at all if this solvent is a better solvent? We believe the difference is how the polymer, what the polymer morphology is inside of the gel. So essentially, if you have the poly-THF, which is more hydrophobic, and contact with this polar solvent, it's going to start to approach more of like the nanostructured phase, where the polymer chains are going to come together, and then we have more channels that are totally liquid filled. So you have a less probability of the ion going through a larger solvent channel and getting stuck on the plastic, essentially, when it's moving. And so this is really, really complicated system. So the interactions between the ion, the solvent, and the polymer matter. If you start to add inorganic materials in, then you have those make composites. Then you have those surface interactions as well. And I don't have time to talk about composites today, but I will say that in composites is exactly the same. So all the interactions between all of the ions with the inorganic surface, and then that compared to all of the other things, composite media are really important. So up till this point, all the work we had been doing on the single ion conductors was traditional like X tissue fabrication. This is what most of the field does, especially if you're a polymer scientist. So polymer scientists, we like to make nice polymers that we can characterize really well, and we know exactly what they are. And so that means we usually do polymerization in a really controlled manner. And then we carefully characterize our products. And as I told you, for one of those polymers I pointed out in the literature, we often use multi-step, expensive synthesis routes because we can, so we can make very novel materials. And the other benefit of this is when we make a material and we purify it, we know we remove the impurities, okay? So that won't affect your electrochemistry. But the whole problem with this is if you're going to actually then apply these materials, right, in real devices, we totally have to change the battery cell assembly, right, and manufacturing processes. And so we were approached by a company who's been pursuing in situ fabrication. So with this method, which others have worked on as well, and there's some literature, polymerization occurs inside the battery of copper cells. So you can imagine that you infiltrate the monomers that form polymer into the cell, and then you cure it and form the polymer afterwards. So the downside of this is that the monomer solubility and the miscibility with the things in your electrolyte limits the type of materials you're able to make, right? So we do polymerization outside of the cell. We can use any solvent we want to get that reaction to happen. But inside of the cell, of course, you can only have the materials that are okay to be in the battery. So that limits. The other thing is we can't purify the material because it's already in the battery. So there's definitely going to be byproducts of the chemistry in there. And if you're doing reactions inside of the cell, so there's reactive things in there, and this can impact your surface chemistry. The other big difference is that solution infiltration is super important. So you start adding things into your electrolyte and change the viscosity. So this will then change how the materials get into the porous electrodes or into the separator. But if you do this carefully, it's possible to keep, your cell assembly and your manufacturing approaches really very similar to current. So it could be kind of the next step in reducing the amount of liquid inside of the cell and increasing, to decrease the plastic content. And so we started looking at this. And the company was really interested in what could be achieved with commercially available materials, or materials that were really close to commercially available. So I just told you about how we had been looking at macromonomers. So those are short, very short polymers. We call them oligomers that have reactive handles on them. So these are acrylators. And there's a lot of different macromonomers that you can buy commercially. And so shown here, this is polypropylene glycol. This is PDMS, so polydimethyl siloxane, in two different forms we looked at. We also looked at our perfluorinated polyether. And the reason why we looked at these, along with the poly-THF, is in all cases, they have a lower oxygen density than PEG, and so we thought they should give higher ion conductivity. And we looked at the cases where we used this ionic monomer here. So instead of conventional salt, we use this salt here, which again has a polymerizable handle on it. So we could try to polymerize the anion into the polymer network. And so to reduce the motion of the anion to get higher cation transference. And so at the beginning of this project, we actually didn't know if any of this would work at all. So we didn't know if it was possible to dissolve these macromonomers into the carbonated solvents that are used in commercial lithium-ion batteries. And we didn't know how well the ionic monomer would dissolve, and then we also weren't sure about the ability to work on separator materials. So all of those things have to work, or these systems can't be used at all. So we found that actually most of these are soluble in carbonate mixtures. We looked at ECDC, EMC mixture. The PPGDA, the poly-THFDA, and the perfluorinated polyether were actually very, very highly soluble. We went all the way up to 50% polymer, they were soluble. But PDMS has limited solubility or miscibility. And then we also found separator chemistry to be a big challenge. So commercialized, like cellular separators, polyolefin separators, in a lot of cases we saw wetting issues. So once the solvent had these types of materials dissolved on them, it would sit on the surface of the separator, the drop on it, and it wouldn't easily let. So we knew there were some issues. We found that electrospun PVDF, which was made in my colleagues' lab downstairs, the young group lab, we found that these materials were easily wet with all of the liquid mixtures. So we used this PVDF electrospun mat as kind of our separator material. And we first looked at the conductivity of these gels. And what we found was uniform across the board. We looked at like changing a whole bunch, kind of a wide parameter space. We looked at like the weight percent of the total amount of monomers in the solvent. So going higher weight percent is lower amount of conventional solvent. And we looked at changing the amount of ionic monomer in there. And then the chemistry of the macro monomer was our main thing. And overall, we found that what we had seen before for the ex situ polymerized gels helped for the in situ polymerized ones. So if we use macro monomers that have lower binding energy to lithium, they have the highest conductivity for the gel case. And you can see the conductivities vary by kind of like order of magnitude here. And we're in the range of like above 10 to the -4 at room temperature. And so the ones that perform the best in terms of conductivity were the perfluoropolyethers and the PDMS. And we also tried to figure out, you know, these materials don't necessarily have to be pure single ion monomers. Because if the ionic monomer salts, excuse me, if the anion, all the anions do not polymerize, if they do not react into the polymer network, then they would be mobile in the solution. So unity transference number is not guaranteed. Unfortunately, using the electrochemical method, the Bruce Vincent Evans method, the Bruce Vincent Evans method is really challenging with these types of materials because the carbonate solvents are so reactive. And so we tried that method as well as NMR, as well as some elemental analysis. And we can predict that the ionic monomer binding fraction is at least at minimum 65%. So there may be some mobile anions in there. That's still kind of an open question. We looked at electrochemical stability using a couple different methods. So this is linear scan voltammetry and chronoamperometry. So we found here that, so in linear scan voltammetry, interestingly, you see that it doesn't really seem to matter, okay? Whether the polymer is based on PDMS or PFPE, they appear to have like roughly the same electrochemical stability. There's some small peak around 4, but then they're basically stable to 5.5. We were surprised by that. But then our industrial collaborators suggested we do a more rigorous test, okay? So where we held the potential for steps, I think these were a few hours at a time for each step, we would hold the voltage. So that gives it more time for decomposition reactions to occur. And in fact, when we found that we did that, in both cases, their perfluorinated polyethers have more current, so they're less electrochemically stable at higher potentials than the PDMS. And then our collaborators provided us with industrially relevant electrodes. So these were high loading graphite anodes and high loading C811, so high voltage cathode materials. And we prepared cells with these very, very dense electrodes with this in situ polymerization. And we found that, so overall, our cathode utilization is fairly low, okay? But they were actually really impressed with the cathode utilization that we got because there's no dissolved, conventional salt in these. So that means that the only electrode particles that can actually be accessed are the ones where the plastic is nearby, unless there's any ionic monomer that's not polymerized. So the infiltration of the gel into the electrode is very important for these cycling studies. The other thing we found is that despite the fact that the PDMS and the PFPE gels had roughly the same bulk ionic conductivity, that the PDMS-based gels had way better rate capability. And if you do the math, you'll find that the rate capability was way lower than you would expect from the bulk ionic conductivity in both cases. But the difference was much more substantial with a perfluoropolyether. So what we can say from this, and we also did a lot of impedance studies, we made lithium metal cells, and the same thing held where the perfluoropolyether interface with lithium metal is much more resistive. We can say that the chemistry of the electrode-electrolyte interface is really, really important. Okay, and it really impacts rate capability. And by adding in these polymers, even though we often imagine that polymers are kind of pure inert, it really, really impacts the surface chemistry and the SEI that's current. And then that's really important. So that's something that we should keep in mind in the future. Okay, and so I'll finish this by saying that we've been looking at these single ion conductive gels. And I didn't tell you about composites, but we've also looked at composites. And we find that these materials are really strongly influenced by all of the chemistry of all of the components in the system. So they're all important. Even if the ones we want to ignore, they're all important. And processing is also really important. I'll just tell you that. And then I will say, I showed you a little bit of what we did with Raman spectroscopy. For other systems that I didn't show you here, sometimes we see huge Raman peak shifts with changing the materials or the solvent environment. I think there's still a huge characterization challenge to be done in understanding what the spectroscopy means, probably by comparing it with simulation. But you can get decent conductivity for single ion conductors as their solvent with cheap formulations with things that are commercially available. Interface chemistry is really, really important, and safety is still an open question. Okay, so with that, do you want me to talk about freeze, or do you want me to go on the other stuff? Okay. I will skip this. If you are interested in concurrent electron ion transport, I would encourage you to take a look at this paper that we published last year. So we've been looking at solid state electrolytes. These don't have polymers in them. So these are all inorganic, where you have, well, there's some organic material that are crystalline, where the organic material is an electron conductor. So we've been looking at, and we have ion transport that's essentially facilitated by electron transport. And this is a new area, and there's a company, Ionic Materials, that's been working on similar type materials. But we have a paper out about mechanism of conduction in those. That's pretty interesting. Okay. All right. So I was asked to tell you about myself. And I want to commend the student chapter for making this request. This is actually only the second time I've ever been asked to talk about myself when I've given a seminar. And surprisingly, the first time I was ever asked was in January of this year. Okay. And so this is good. This seems to be becoming a new trend, which I think is really healthy. So I don't have any excellent family pictures. This is the last family picture I have. So I have a family of 5. I have 3 children. And we took this selfie when we were traveling over the Christmas holiday. We stopped at the Corning Glass Museum and we took this selfie. And it is very hard to get a good selfie with people that are different sizes. This is what I've learned. This is a technical challenge I need to overcome. Okay, so about me. So I was actually born in this area of New York State, which is a very, very rural area, in a place with more cows than people. And I did my undergraduate studies at Widener University, which is a small college outside of Philadelphia. And I went there because the faculty there they teach That's what I do. And I had the opportunity to do undergraduate research as well. My degrees are chemical engineering and chemistry. And then I had my oldest son was actually born while I was here in Pennsylvania, Matthew. And then I moved to Cornell for my graduate degree. So I imagine a lot of you are graduate students. And I didn't know, I was really interested in materials chemistry, engineering. That's what I tell people I was really interested in. And I ended up in the Archer group, and my dissertation was kind of a two-part thing. So we were making a new class. It was a new class of materials at the time. So nanoparticle organic hybrid materials. So these are nanoparticles, very, very densely crafted, short polymer chains or organic chains, such that the material actually behaves as a fluid. So if you have a material and you flip it upside down, it could flow. If it had enough organic in it, but there was no solvent that failed. And they were hybrid materials with particles, very nano structured materials. And we were studying them as battery electrolytes. Battery electrolytes because you get to the viscosity of these solvent-free materials. And so I did a lot of synthesis work and then basic materials characterization work as a PhD student, and then I did a lot of electrochemical characterization. And I made lithium metal batteries, and I studied lithium metal electrode deposition. Tried to understand it in the context of the transport properties of the fluid. And as a graduate student, I always thought I would go to industry. So when I started my fifth year, so I've been at Cornell for 4 years. My program that my daughter was born, so Celia this year. So she was born at that time, and then I started to look for industry positions. I actually applied for jobs in upstate New York, in Ohio, Pennsylvania, and Delaware. I had an interview with Dow. I had a phone interview, and I didn't really get anything that year. So then the following summer, and I applied maybe to like 30 companies, right? And I didn't get any job offers. My research was still like ongoing, and I was busy in the lab, and I was really happy, and everything was good. I decided to apply for a postdoc fellowship at NIST, which is a government laboratory in Maryland. And then, I saw a job posting for a faculty position in Buffalo, New York, actually. And my brother lives in Erie, Pennsylvania here. So I was like, oh, that's really close to my brother. I asked my advisor, like, what do you think about me applying for faculty positions? And he was like, timing is great. You should do it. He was so supportive. And I was like, oh, no, it is a lot of work to write a faculty application package, folks. So I did that to get to write statements. And I was finishing my dissertation at the time. And so I started to prepare to do that. And then I thought I was like, I'll never be competitive. I was so worried about not being competitive. It was August. Not being competitive for those jobs that I was applying for. I never had a teaching experience. So in my graduate studies, I was very fortunate. I was in research fellowships. I never was a TA. I had no teaching experience. And the local community college had an opening for a chemistry instructor. They were like, they had no one to lecture. So I went for an interview and they hired me in 7 weeks to teach a class in the evening. And my graduate advisor was very kind and let me do this. So I taught chemistry in the evenings my last semester, 3 hours night class once a week. And so I had something to put on my resume. Looking back, I don't think it really made me more competitive. But at the time, I was like, I want to do this, right? So I did that, and I put in applications, and I defended my dissertation right before Thanksgiving in November. I went to MRS in December, and turned in my dissertation before Christmas. And in December, I started getting phone calls for interviews. So I did faculty interviews. I started in January, and then my family, so there were 4 of us, so we moved to NIST here in Maryland. And I did more interviews before I started at NIST, and then a few more in like the first few weeks I was there. And then I decided to go to Notre Dame because I was really excited about, we had a huge faculty hiring initiative in chemical engineering, and they were really trying to add more people in the area of sustainability and really excellent equipment there, and really nice facilities. And I have no family in the class. We have no one here, but we decided that this was the place that we should be by the third start date. This is very common for faculty positions. They don't think you can teach right away, you can defer your start date. So I stayed at NIST until July 20 or June 2015. So I was there for 17 months as a postdoc. That's a really short postdoc. I had my own project that I kind of come up with myself because I had a fellowship, and then my advisor, who was a group leader, which means at NIST, if you're a group leader, you don't really do research, you do mostly administration. He was very busy, but he would get a lot of phone calls from people that wanted to collaborate. He would send us materials. So I had the opportunity to do studies on their materials. So that was a nice plus for my postdoc. And I also got to do what I went there to do, which is I thought being at NIST, I could learn about some new materials characterization techniques that were special for them that I wouldn't otherwise get exposed to. So the neutron facilities there. So I was able to do some neutron scattering measurements. And I was really competitive in the group who was really experts in characterization. So I got to learn about different research problems and different new tools so that I know about more things. So that was really helpful for starting my career. I also got some time to learn some more organic synthesis because that was important for my group too. They let me do that. So I've been in Notre Dame since then. And if you haven't got the chance to visit our campus, I would encourage you to do so. And I always appreciate when I get to come down here. And then Eli was born my first year at Notre Dame. So that's my family and that's me. And thank you so much for inviting me. Happy to watch.
Question?
Okay, so I think I'm having a hard time hearing it, but the first question. What characterization? So in situ characterization tools specifically for things. That's a good question. So I think there's been some long-standing tools and some upcoming tools. I mean, liquid solid interfaces are easier. So very solid interfaces are much harder as well. Liquid solid interfaces, I think there's a lot of tools that can be used. And so optical spectroscopy has been pretty successful. So there's different optical spectroscopy techniques that are surface sensitive. So like FTIR, like reflection, we can get surfaces. So there's now also a lot of like beamline capabilities, right? So, but not necessarily as surface sensitive if you're going through the whole place. So I still think there's gains to be made there. I think you know, spectroscopy is a good tool. Of course, there's always a challenge. So in-situ TEM has come a long way as well, but I think, you know, looking at the interface chemistry, still challenging. Although you can do some more in-situ TMPA. So, is there another question? So we haven't measured the viscosity of the. So I think a couple things matter in terms of wettability of the electrolyte and the electrolyte. So viscosity is one of them. But also chemistry, right? So surface effects and wettability are important. We haven't specifically measured the viscosity of the infilling solution, right? So like the pre-polymer solution. I would say the mechanical properties of the gels themselves vary wide. So you can pretty much get whatever you want. So the mechanics of gels changes based on the polymer chain chemistry, the length between the crossing nodes. So for the monomers in the solid state, as well as when they're spout, and how it's moving spout. And the other interesting thing about gels is that they're not really softer when they have more fluid in them. Because if you think about you take a cross-link network, and if you fully scrub it, so you scrap all the fuse as far as they can get apart, and those materials, those gels become very good temperature. So the mechanics are very, very different. And yeah, they can vary. So I would say moduli from like 10 to 5, 10 to 6. That's pretty common, but you can get systems that are much more stiffer or much more softer and more like polymer materials if you're creative, especially with the network.
So I have a question regarding the interface form. So I mean, from the presentation, I was saying that if we have a master survey, which is better from the time, but actually, I think if we have a master survey, then the same form may be
yeah, so I agree with you. So what I didn't show was the data that we have on the formation cycle. So when we first charge these cells. So we see that the formation cycles are really sensitive to what's in the electrolyte. And current to pass it's a different. So looking at the first cycle formation data, which a lot of people kind of like ignore because it's like Proctor cycling, that can be really useful in trying to figure out exactly what reactions are happening. I would say I agree that I think the lithium solvation cells are important, but the other thing that's different is these systems, right? They don't have any conventional anions. And I would say that for long term, like I said, anions are decomposing, it's not good for them to be in the interface. But I think a lot of our conventional batteries, the SEI that's formed in them is partially the product of anion, right? So like the S6 decomposes or releases a lot of chloride. So you get some chloride rich components in the SEI. So if you change how it's solved, you have different anions in there, and they're decomposing differently out of the other thing, and I didn't tell you this, was that we did our formation cycles of the first charge before we actually poured the gel. The reason why we did that is the company has suggested if you do the formation cycle first, well, then you don't have a problem with the small molecules and making service and make the SI. But what you do have then are a lot of reactive groups. So you have a lot of activated groups, a lot of vinyl groups, and things that are more reactive or present when that formation is happening. And think that actually perhaps the fluoroether monomers that they actually pour itself begin to self-initiate polymerization during the formation cycle. So it's an electrochemically initiated polymerization process. So what we do is we charge the cell, and then after the formation cycle, then we would heat it or cure it and make it cell. We think they're actually three each other. And that's who make it. But of course, as the vinyl groups react with those fast surface, you're going to have a carbon rich, interface, right? And some other different. So I think these are all, there's a lot of important